after reading this, you realize that it's a typical 6 plus 1, 7, and then 3, and then 7 type of situation. And we will use this problem to cover the mathematics involving HCP. The first problem you can try, the first question you can try, the number of atoms in this HCP unit cell is. Maybe this particular figure can help. Focus on these 3 fellows, 6 and 6, 1 here and 3 here. Those 3 are completely inside. Those 3 are completely inside. So those 3 will be 3 effectively. Now focus on the center and center. How much will they contribute to the cell? Top, middle, and bottom middle. How much? Half or 50%. So 2 fellows, half. Now focus on these 6 and these 6. How much contribution by those 12? Well, think like this. You have an apple. That apple is cut into half. So when you're looking at it, you have half apple. And then on that half apple, you are making 120 degree. 120 here. If I can show you the top view of the apple, then this angle will be 120. 120 degree of the apple are inside the cell, and 240 degree are outside the cell. And we are talking about half of the apple. That's right. Half into 1 by 3. Half into 1 by 3 is 1 by 6. If you need further explanation, raise your hand and I will try to explain further. Alright, first thing is why half? Because of the bottom side cell. First you need to visualize the surface, which is the bottom surface of the hexagon. That hexagon is forming a surface, right? And on that surface, in one vertex, you have an apple. On one vertex of that hexagon is a surface, and on its one vertex, imagine one apple. That plane of hexagon will cut that apple into half. One piece above and one piece below. The unit cell is above that hexagon. Below the hexagon is a different unit cell, or different unit cells rather. Now you are left with half of the apple, and in that half of the apple you need to focus on this angle. I hope you are looking at the pointer. Only 120 degrees belong to the cell, 240 degrees belong to other cells, neighborhood cells. So half into 120 degree by 360, which is 1 by 3. Half into 1 by 3 is 1 by 6. Any more question? Let me know. So can you select the answer now? The answer is B. And now, this is an easy one. I think this you can answer straight away. The empty space in HCP unit cell is. We talked about FCC, we talked about HCP. In both of them, packing is 74%. So if the packing is 74%, 100 minus 74 should be the answer. And that answer is option D, 26. And now comes the most difficult part. The volume of this HCP unit cell is. Now, how does one calculate the volume? If you look at a cylinder, why is it pi r square into h? It is the base area, which is pi r square multiplied by the height. Base area multiplied by the height. In this particular drawing, look at the pointer. In this particular drawing, you have a base area which is the area bounded by a regular hexagon. So that base area we can find, and then we multiply that by the height. Here, height is also not known. That makes it even more challenging. We are only given the radius of sphere. That's it. Yes, but the good thing is that spheres are all identical. Identical spheres, each having radius r. That's the only information given. And if you look at the answer also, there's only r and no other variable. So, how does one find the height between the top hexagon and the bottom hexagon? The top hexagon and the bottom hexagon. And for that, the tetrahedral void concept will be very useful. Tetrahedral void concept will be very useful. Look at the pointer where I'm showing it right now and where I'm showing it right now. Think of this as D for a moment. And the top is the middle. Top is the middle. This fellow is this fellow. And this fellow is going to be placed over these three. It will be touching these three. If you remember the layering discussion, then that's how we got HCP structure. It was about hiding tetrahedral voids. HCP was about hiding tetrahedral voids. So this ball is over this gap. So from once this ball is placed, you will have something like this. Let me try to show it. What we call as the height of tetrahedron. Height of tetrahedron is this. and that will be this once it is placed here. So that will be this, or that will be this. I'm talking about this. This is the height of tetrahedron. This is the height of tetrahedron from here to here. These three are these three, like that. Okay, these three, and then you have the height, this height or this height. So clearly, if you think of these three balls and then fourth comes from the top, and then we are talking about this height h, but likewise we can think from the bottom also. Bottom A, if you see, then look at the center one, that ball from the bottom, so that h, bottom also will have h, height of tetrahedron, top also has h, bottom also has h. So from top to bottom, top hexagon layer, top hexagon and bottom hexagon, the length of that is going to be h plus h, which is 2h. And then if you know the base area is very easy, that you can find out. And we will discuss that. So once you know the base area, multiply that by this 2h, and you have got the result for the volume. But what is h? Now that is something that you need to memorize. For tetrahedron, what is the formula for height? If anybody knows, then tell me. If you know the formula for height of tetrahedron, or I will give it to you. So you may like to note it down. It is root 6 by 3 times edge length. Root 6 by 3, 3 is outside the root. 3 is outside the root. Root 6 whole divided by 3, and A is the edge length of the tetrahedron. That's the formula for the height of tetrahedron. But A is the edge length, and in this question we are just given radius. We are just given radius here. So can you tell me what is the relationship between A and radius? A and radius. That's a very simple question. Look at the balls here. Or it will become even clearer here in this drawing. This was this edge length. This was edge length, right? Edge of the tetrahedron I'm talking about. Edge of the tetrahedron. So A is going to be 2r. So height of tetrahedron is given by root 6 by 3 times twice of r. Okay? And we want the total height of the hexagon, I mean of HCP, and that will be twice h, which is 4 root 6 by 3 r. Okay. Now let's proceed with volume calculation. So we have a hexagon. In hexagon, two balls are touching each other. So clearly this will be A. I mean A or 2R, whatever you like. 2R, 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 2R. What is the area of that hexagon? Area of hexagon. That's the simple question. So we can construct 6 equilateral triangles. This is 2R, 2R, 2R. So area of one equilateral triangle, √3/4, side square, and volume is the base area. Base area multiplied by the height, and the height was 4√6/3R. 4√6/3R. Just simplify this. And tell me what should be the correct option. You can change the board and you can see the option. And the answer I have is option A. Yes, I can see that private message. Yes, I can see that private message. We know the volume of all the spheres. Yes, we know that. We know the packing efficiency also. Yes. So we can calculate the volume occupied by hexagon. Yes, that's right. You can do that. But remember that 74% is not accurate. 74% is not, I mean, it's close, it's very close, but it's not exact for packing efficiency. So just do that and see how much you are getting. If any other option is close, it could be a problem. You are getting 33 R³ by that method. Okay. So if you are getting 33 R³ by that method, then let us check the options. Option A is 24 into √2, which is 33.94. 33.94 and 16√2. Okay, that is way off. That you can reject. 22 point something. 12√2 will be way off. That you can reject. 64/3√3. Okay, even that is quite distance away. 12.3 something. Yes. So that's a good idea. Very good idea actually. But anyway, you have to know that math which we have done. In some other problem it may come. Any other questions? If you have, then let me know.
This is an alternate approximate solution. Packing efficiency is approximately 74%. So if the volume is V, then 74% of V will be equal to the volume of 6 atoms. We have already found number 6. On solving this, you will get V equal to approximately this much. You can get more accurate answer by alternate solution if you know that packing efficiency is pi by root 18. So V multiplied by this will be 6 times volume of one atom. And this gives us accurate answer for volume.
Another challenging problem. Now, while this looks like a two-dimensional problem, well, it's about two-dimensional arrangement. So those things are out, simple cubic or BCC or FCC. You just have a table in front of you and you are given some balls. You just have to go for one layer only above the table. That's it. It's a 2D situation. And you want to maximize the space. You want to maximize the space. That means it's linear arrangement. Another line that should come, you should try to cover those dips. That way you can maximize the efficiency of packing. So in the next line, this is obvious. This is an obvious choice. Now we have length 40, 10 plus 10 plus 10 is 30. Okay, so that means I can have one here also, and I can have one here also. Now what will happen is that the boundary of the square will pass through this, it will pass through the center of it. Square will be something like this, going like this, going like this, and then like this. Now when we try to cover these dips, we are replicating this line. That means like this. And then when we try to plug these gaps, again we are replicating this line. That means something like this. Vertically, let's see how much have we gone. This is 5 plus, I think there should be some scope. Or anyway, let me draw one more line, then we will see whether it will fit into the square or not. More than that is not possible because of 40. So how should the square be? For this 10 plus 10 plus 10 plus 10, there is no doubt that it could be like this, for this. But for this, we may have to check up. Will it be able to cover this? Will it come within this? We will have to do some math. It's a math problem basically. So to know up to where the square will go, maybe we can find the height of this triangle. And then opposite triangle will have the same height, argument of symmetry. And then one more triangle, again argument of symmetry. So finding the height of these triangles will give us some idea up to where will it go, this square. That should be easy. This 5 plus 5 is 10. 10, 10. What's the height of an equilateral triangle whose side is 10? Five root 3. Five root 3 means roughly 8.5. 8.5, 8.5, 8.5, 8.5. 34. 34, okay. So that means square will go beyond that. 34. 5 root 3 is 8.66. More accurate calculation. 8.66 into 4. 34.64. That's more accurate. So from here to here it is 34.64. And this radius is 5. Okay, 34.6 and 5. You can say nearly 40. So this figure is nearly correct. 39.6 it is coming out. 39.6 up to here. So slight 0.4. That is 0.4 mm. This gap. So we ignore that. Four completely inside. Completely in 1, 2, 3, 4. Completely. Now those tick marks are completely inside. $14. Then half of fellows. 1, 2, 3. Oh, here also. Half. 18. 18 spheres are there. Number of spheres per unit area. Area is how much? Forty. 4 by 4, that's a centimeter. 16 centimeter square area has got 18 balls effectively. And therefore, 1 centimeter square, 18 by 16. 18 by 16 should be the answer. Very close answer. 1.125. While we were always concerned with 3 dimensions, if you want to increase the efficiency in 2-dimensional layering, then this is the way you should go. If you recall our layering discussion for 2 dimensions, then this is what we discussed. This is what we discussed. Left was square close packing, right was hexagonal close packing. And efficiency is more in hexagonal. And that's exactly what we have done in this problem. Hexagonal packing we have done in 2 dimensions here.